Hi everyone, welcome back. In previous videos, we've been focusing mainly on vaporization and condensation, but in this video, we will discuss other phase changes and do some calculations associated with that heat energy transfer. So, sublimation is when you go from a solid to a gas. And so if any of you have ever played with carbon dioxide or dry ice, you would witness it going from a solid to gas. It sublimes at room temperature. And the opposite of sublimation is deposition. And that's when you go from a gas to a solid. And we don't really witness deposition happening often, although one of my favorite organic chemistry labs is when we sublime caffeine from tea, but then to capture the little caffeine that we've isolated from the tea, we use like this cold finger. And so we sublime the caffeine to separate it from some of the pigments and chlorophyll, etc. And then it captures onto what we call a cold finger. We put dry ice in it, it's super cold. So the caffeine deposits on what we call the cold finger, and then you can collect the pure caffeine crystals from there, which is super cool to witness that depositioning happening. Because it's just like this vapor, and then it forms these really beautiful crystals once it reaches the cold finger. Another example of sublimation happens in your freezer at negative 10 degrees Celsius. And freezer burn is essentially, like, if you ever heard the term freezer burn, and that basically, if you're storing meat in there and you're like, oh, it has freezer burn, then it's probably not super tasty. And that's because it is essentially the dehydration of that meat when the water sublimes. So water is just subliming at that temperature of your freezer, and that's where we get freezer burn from. All right, we will not be focusing on sublimation and deposition in my class. It's something that doesn't happen for all substances. Like iodine can sublime. Like I said, caffeine can do that at higher temperatures. Dry ice does it at room temperature, but not everything undergoes sublimation or deposition. So we're mainly focusing on vaporization, condensation, and also fusion and freezing, right? And those are where you're going to be doing your calculations with. So what is fusion? Well, fusion is just another way of saying melting, so also known as melting. And that's when you go from a solid to a liquid. Now, is this process exothermic or endothermic? Think about what you need to do in order to melt ice. Yeah, you need to apply heat energy. So this is an endothermic process. Very good. And therefore, the sign for enthalpy will be what? A positive enthalpy. Excellent. Now, freezing is when you go from a liquid to a solid. It's the opposite of fusion. And therefore, those liquid molecules need to lose some of that thermal energy in order to become a solid. And therefore, this process is exothermic, which has a negative delta H. Let's represent this using that chemical reaction notation, even though this is not an actual chemical reaction, it's just a physical change taking place. So going from a solid to a liquid, we need to apply heat. And And like we learned with condensation and vaporization, there is an enthalpy associated with each substance. So you would look up the enthalpy, not of vaporization, but of fusion for water at 0 degrees Celsius, right? Its freezing point. And we said that this is a positive, and in the literature is 6.02 kilojoules per mole. Now, the only one you would find is this number here, the positive number, because it is understood that the opposite process, freezing, requires the same amount of energy per mole of water. However, you need to lose heat, and therefore you look up the enthalpy of fusion. There's no enthalpy of freezing. Look up the enthalpy of fusion and then do what? Excellent. You would change the sign. It's negative 6.02 kilojoules per mole. Fantastic. All right. I wanted to show you a video showing you the heating curve for water. And I also want you to understand, it's a nice visual, and so we'll watch that together and we'll discuss it. And then we'll work a problem involving a heating curve. But also know that you can do the same type of calculations for cooling curves. You would just need to change the sign for the enthalpy, right? And so instead of getting positive heat energy, you'd be getting a negative heat energy because you're cooling. So just understand that even though I'm showing you for a heating curve, make sure you're practicing your homework, which will also have you answering questions regarding cooling curves as well. But same principle, same theory applies, okay?
Hello. In this video, you will learn about the heating curve for water. This curve shows how water heats up and undergoes phase transitions from solid to liquid and then from liquid to gas. A heating curve is a graph that shows the temperature of a substance as you add heat to it. We start the heating curve with an ice cube containing 1 mole of water at negative 25 degrees Celsius. As you begin to heat the ice, its temperature rises in accordance with its heat capacity. The specific heat capacity of ice is 2.09 joules per gram degrees Celsius. So, the total amount of heat to warm the ice from negative 25 degrees Celsius to 0 degrees Celsius is Q equals M times C ice times delta T. Substituting into the equation, you get 18.0 grams times 2.09 joules per gram degrees Celsius times 25.0 degrees Celsius, which gives you 941 joules or 0.941 kilojoules. When the ice hits 0 degrees Celsius, it begins to melt. At this point, all of the heat goes towards melting the ice, not towards warming it. So the temperature flattens out and remains constant as the solid ice converts to liquid water. The amount of heat required to melt the ice is determined by the enthalpy of fusion for water, which is 6.02 kilojoules per mole. And we calculate it as Q is equal to N times delta H fusion, or 1.00 mole times 6.02 kilojoules per mole. Moles cancel and you are left with 6.02 kilojoules. Once all of the ice is melted in liquid water, the water can begin to warm again. Now, however, the heat capacity of liquid water, which is 4.18 joules per gram degrees Celsius, determines the temperature change as you add heat. The total amount of energy required to heat the water to its boiling point, which is 100 degrees Celsius, is given by Q is equal to M times C water times delta T. This equals 18.0 grams times 4.18 joules per gram degrees Celsius times 100.0 degrees Celsius. Grams and degrees Celsius cancel, and you're left with 7.53 kilojoules. When the water hits 100 degrees Celsius, it begins to boil. At this point, all of the heat goes towards boiling the water, not warming it. So the temperature again flattens out and remains constant as the liquid water is converted to gaseous steam. The amount of heat required to boil the water is determined by the enthalpy of vaporization for water, 40.7 kilojoules per mole, and we calculated it as Q is equal to N times the enthalpy of vaporization, which is 1.00 mole times 40.7 kilojoules per mole, or 40.7 kilojoules. Once all of the water has evaporated into steam, the steam begins to warm again. Now, however, the heat capacity of steam determines the temperature change as you add heat. The total amount of energy required to heat steam, or gaseous water, to 125 degrees Celsius is given by Q is equal to M times C steam times delta T. The heat capacity of steam is 2.01 joules per gram degree Celsius. Okay, here's a question for you. How much heat is required to warm the 1 mole of steam, 18.0 grams, from 100.0 degrees Celsius to 125 degrees Celsius? The heat capacity of steam is 2.01 joules per gram degree Celsius. A, 0.905 kilojoules, B, 4.53 kilojoules, or C, 0.0502 kilojoules.
All right, we're going to stop right here and make sure you do this calculation, and the correct answer you would get for it is A, 0.905 kilojoules. All right, so let us summarize a little bit about what we learned before we practice a problem together. So if we are doing a phase change, as you saw in the video, when a phase change is occurring, temperature is not changing. And therefore, you see a plateau. There's no slope, which indicates you have a plateau. And the equation you use for a phase change to calculate the heat energy, either added or removed, depending if it's a heating curve or cooling curve, is Q is equal to N, the number of moles, times delta H. And I discussed this in my previous video, if you remember the problem I worked where water was condensing on the surface of an aluminum block. I was really specific to say water is only undergoing a phase change, condensation, in that example. However, the aluminum block was changing temperature. And so that changes the formulas that you use. Okay. And so, if the amount of heat required to heat a single phase in which the deposited heat raises the temperature, because we're talking about heating curve, in accordance with the substance's heat capacity, when you see something that's raising the temperature, right, or cooling, lowering the temperature, right, whenever we see these temperature changes, right, and you can calculate, for example, delta T is equal to TF minus Ti, final minus initial, then that means your substance is undergoing a change in temperature, not a phase change. And therefore, you use the formula Q is equal to MCAT, MC delta T. All right, so let's go ahead and work a problem together using all this knowledge. Okay, this question is asking us how much heat is evolved in converting 1 mole of steam, so that's our starting point, at 145 degrees Celsius to ice at negative 50 degrees Celsius. The heat capacity of steam is 2.01 joules per gram degree Celsius, and that of ice is 2.09 joules per grams degree Celsius. And so when you hear steam and ice, what type of molecule are we working with here? Good, we're working with water. That's important, because the constants that you have to look up, the enthalpy of fusion and vaporization, are unique to the substance you're studying. And so in this case, it's water. And it looks like we're cooling, right? This is going to be a cooling curve, a great example, opposite than what we just saw in the video, which was a heating curve. Okay. All right, so for me, when I do heating or cooling curve type problems, I like to draw it out. You've heard me talk about this before. Try to draw it out when you're trying to solve a problem. And many times when you do that, it'll help you envision what you need to do next. So I'm going to draw a graph. Okay. And for heating or cooling curves, on the y-axis is temperature. And we're working in degrees Celsius here. And on the x-axis is the heat energy. And we will just write heat removed since we're cooling it down. If it was a heating curve, then we would say heat added. And this is in kilojoules per mole. And then I always like to mark the starting temperature. So the starting temperature is 145 degrees Celsius. And then when steam cools down, it's going to hit the boiling point. So you always want to mark the boiling point, whatever that may be. We know what it is for water, but you could be doing the same type of calculation for ethanol, for example, or acetone. So it's important that you look up the boiling point if it's not already provided for you, and also the freezing point. Okay, so boiling point we know is 100 degrees Celsius. And then it's going to cool down and hit the freezing point, which for water is 0 degrees Celsius. And then the coldest temperature, the final temperature, is negative 50 degrees Celsius. So I like to mark those temperatures on my graph. And so we're starting at point here. And I'm just I'll label it in a second, but that's the initial temperature, and then it cools down and reaches 100 degrees Celsius. All right. And then this is step 1 right here. That's step 1. And then once that steam cools down, and then what does it undergo? What type of phase change? Excellent. It undergoes condensation, right? We're going to go from a gas to a liquid. And remember, there's no slope with the phase change. And so that's step 2. Whoopsie. Step 2, that's when we go from a gas to a liquid. And then it cools down all the way to 0 degrees Celsius where it starts to freeze. And that's step 3. And then it freezes, it goes through a phase change. And then it cools down, and that's step 4. And then it cools down to negative 50 degrees Celsius as solid ice. And that is step 5. So from here, it's a liquid to a solid. Those are the 2 phase changes taking place. So as you can see here, we have 5 different calculations to set up. Let's write down our given information that we will utilize. So we are given that we have 1 mole of water. And in the form of steam. And initially it's at 145 degrees Celsius and goes all the way down to negative 50. The heat capacity for steam is equal to 2.01 joules per gram degrees Celsius, and that of ice is 2.09 joules per gram degrees Celsius. And let's just go ahead and get started. So, step 1. We are, there we go. In step 1 here, are we undergoing a phase change or a change in temperature? Excellent, we're undergoing a change in temperature, so what formula will you use? Great, Q is equal to MCAT, right? So I'm going to write down those two formulas just for reference. Q is equal to MCAT for when we have a change in temperature, and Q is equal to N delta H for when we're doing a phase change, okay? So we're going to use Q is equal to MCAT, which means we need the mass, right? So let's go ahead. We have 1 mole of water. I'm just going to do that calculation up here. And the molar mass is 18.02 grams per mole for water. And therefore, you have 18.02 grams of water that we're cooling down through this whole process, right? And so Q is equal to 18.02 grams times the specific heat capacity for steam, which is 2.01 joules per gram degrees Celsius, times the change in temperature. And I put that in parentheses. Change in temperature is always final minus initial. And so in this case, the final temperature is 100 degrees Celsius, the boiling point, right? And the initial temperature was 105 degrees Celsius. And when we do this, we get negative 1629 joules. And I will go ahead and convert this to kilojoules, because in the end, we'll give our final answer in kilojoules, as noted here in the word problem. So let's make our lives a little bit easier and just go ahead and convert. How many joules in a kilojoule? 1,000. Fantastic. So you would divide that by 1,000 and get negative 1.629 kilojoules. Definitely refer back to this later, so I will highlight it, and then we'll move on to the next step here, part 2. Okay, so in part 2, are we undergoing a phase change? Indeed we are. So what formula would you use? Fantastic. Q is equal to N delta H. We're not changing temperature. We have a plateau, no slope. And so, but which delta H would you use? Excellent. You want to use enthalpy of vaporization, because at this point, this is the boiling point. So we're condensing here, but it's the opposite of enthalpy of vaporization. So will the sign be positive or negative? Good, it's negative because in condensation, like we learned in the previous video, we are releasing heat energy. So we have the enthalpy of vaporization. If you look that up, at the boiling point is 40.7 kilojoules per mole, but because we're undergoing condensation, it's a negative 40.7 kilojoules per mole. And so here, Q, and actually I'll say Q1 and Q2, is equal to 1 mole times a negative 40.7 kilojoules per mole, and that is equal to negative 40.7 kilojoules of energy associated with condensation. A lot of energy there, huh? So let's highlight that and save it for later and move on to step 3. Now in step 3, which formula will you use to calculate the heat energy associated with cooling the water down? We definitely see a change in temperature, a slope in that line. So yes, Q is equal to MCAT. Great. So we have 18.02 grams times C, which I didn't provide it here, but I would provide it on an assessment, 4.18 joules per gram degrees Celsius. That is the specific heat capacity for liquid water, which is something you probably saw in first semester general chemistry, 4.18 or 4.184. And we have final temperature is 0 degrees Celsius minus the initial temperature, 100 degrees Celsius. And when you calculate that, you should get negative 7,532 joules. And divide that by 1,000 to get negative 7.532 joules. That's the amount of energy that needs to be lost in order to cool it down to its freezing point, 0 degrees Celsius. All right, Q4. Which formula are you going to use for step 4 of this process? Excellent. Q is equal to N times delta H. But which delta H will you use? Enthalpy of vaporization or enthalpy of fusion? Good. You're going to use the enthalpy of fusion that we just learned about. And will it be positive or negative? Excellent. It will be negative. And just a clue here, just to make sure you understand the signs, is that if you're doing a cooling curve, all your heat energy should be negative because heat's removed. If you do a heating curve, like was shown in the video, then your heat energies would be positive, like all positive. So that's another way to check yourself if you given the appropriate sign to the enthalpy of vaporization or fusion. All right, so we have 1 mole and then times the enthalpy of fusion, which is negative 6.02 kilojoules per mole because we're freezing. And that is negative 6.02 kilojoules. I'll highlight that there. And then finally, step 5. We're cooling it down even more. So which equation do you plan to use? Good, MCAT. So 18.02 grams. Now we need the specific heat capacity of ice, which is 2.09 joules per gram degrees Celsius times the change in temperature, which is 0 minus a negative 50. And you should get, oh, my apologies, let me fix that. It should be negative 50 minus 0. Final minus initials, that ends up being negative 50. And then you get a negative 1880 joules, which divided by 1,000 would be equal to negative 1.88 kilojoules for this part of the cooling curve. Let me highlight that. Fantastic. So this question's asking for the total amount of heat energy that is evolved, or another word would be released, when we convert the 1 mole of steam all the way at 145 degrees Celsius to ice at negative 50. So what do you think you need to do to find the total energy? Excellent. You need to just add them all up. So Q total is equal to each of these steps, Q1 plus Q2, Q3, Q4, and Q5. So we're adding them all up, and you should get a final answer of negative 57. I'm just rounding to 3 sig figs here. Negative 57.8 kilojoules of energy for this entire process. And that is your final answer. So make sure you try to do this again on your own without looking at the answer. Talk yourself through it, reason through it. Once again, first, anytime you start a problem, try to draw it out. And so in this case, draw that cooling curve or heating curve. And then, reason why you chose which formula you needed to use or which literature constant you had to look up and utilize for each step. In addition, when you do a heating or cooling curve, you may not have all 5 steps to calculate. Maybe you just have step 2 and step 3, given whatever conditions your sample is in. So just so you know, it may not be this long for an assessment, but it could be, right? So you can do up to 5 steps. Also be mindful if you're working with water or another substance like ethanol or acetone. There's other different molecules we could be working with, and of course you would be provided the literature data necessary to solve those problems. So like I said, work through this problem again, work through your homework, email me with any questions, and thank you all for watching, and see you next time.